Let's dive into the CMOS fabrication steps, focusing on the process using N-well technology. The entire CMOS fabrication involves 20 steps, but here we'll cover the initial key stages. First, we start by selecting the substrate, which serves as the foundation for the fabrication. For the N-well process, a P-type silicon substrate is chosen. Next, we have the oxidation step. Here, a silicon dioxide layer is grown on the substrate. This SiO2 layer acts as a barrier that protects certain areas of the wafer during the diffusion of N-type impurities. The oxidation is performed in a special chamber where the substrate is exposed to a high-quality mixture of oxygen and hydrogen at around 1000 degrees Celsius. After oxidation, we move on to the photoresist application. In this step, a photosensitive emulsion is evenly coated over the SiO2 layer. This allows us to selectively etch the oxide layer through photolithography, defining precise patterns needed for the next stages of fabrication. These initial steps are crucial to set the stage for building the complex CMOS structures that follow. Now, moving on to step 4, which is masking. This step continues the photolithography process. Here, we create a specific pattern using a stencil that acts as a mask over the photoresist layer. When the substrate is exposed to UV light, the photoresist beneath the exposed areas of the mask undergoes polymerization, meaning it hardens in those regions. In step 5, we remove the mask and the unexposed photoresist, which didn't polymerize, is dissolved using a chemical developer like trichloroethylene. This effectively clears the unwanted photoresist, leaving behind the patterned areas that were exposed to UV light. Finally, in step 6, we proceed to etching. The wafer is placed into an etching solution, typically hydrofluoric acid, which selectively removes the silicon dioxide layer from the areas where dopants need to be introduced. This etching step is crucial because it opens up the oxide layer exactly where diffusion is required for the device fabrication. Now we'll look at the final steps in this process. Step 7 involves removing the entire photoresist layer after etching. The areas of SiO2 protected by the photoresist remain intact, and the mask itself is stripped away using a chemical solvent, usually hot sulfuric acid. Moving to step 8, we form the N-well by diffusing N-type impurities into the P-type substrate through the exposed regions. This creates the desired doping profile necessary for device function. In step 9, the remaining SiO2 layer is removed using hydrofluoric acid, preparing the surface for the next phase. Finally, step 10 focuses on depositing polysilicon. It's crucial to avoid any misalignment of the gate in CMOS transistors, as this could cause unwanted capacitance and negatively impact circuit performance. To address this, a self-aligned gate process is used. Here, the gate regions are defined before the source and drain are formed through ion implantation, which ensures precise alignment and optimal device operation. Now, let's dive into the formation of the gate region. We use polysilicon for the gate because it can handle extremely high temperatures, exceeding 800 degrees Celsius, which is essential during the annealing process for source and drain formation. This polysilicon layer is deposited using a chemical deposition method over a very thin layer of gate oxide. This thin oxide layer is crucial because it prevents any unwanted doping beneath the gate area. After depositing the polysilicon, we remove the excess material everywhere except where the gates for the NMOS and PMOS transistors are formed. Next comes the oxidation process, where an oxide layer is grown on top of the wafer. This oxide layer acts as a protective shield during subsequent diffusion and metallization steps. During masking and diffusion, we create small openings in this oxide layer using masking techniques. These openings allow precise diffusion of N-type impurities into specific regions, forming the required transistor structures. This careful masking is key to defining where the dopants enter the silicon, ensuring proper device functionality. At this stage, we use the diffusion process to create 3 N+ regions, which will become the terminals of the NMOS transistor. Following that, in step 14, the oxide layer that was previously deposited is carefully removed. This is important to prepare the surface for the next set of processes. Then, in step 15, we carry out p-type diffusion, similar to the earlier n-type diffusion, but this time for forming the terminals of the CMOS transistor. Finally, step 16 involves laying down a thick field oxide layer. This thick oxide acts as a protective barrier, covering areas of the wafer where we don't want to form any terminals, ensuring proper isolation and device reliability. These steps are crucial in defining and protecting the active regions on the wafer. Now, moving on to the final steps. Step 17 involves metallization, where we create metal terminals that serve as the interconnections within the device. To do this, aluminum is evenly spread over the entire wafer. Then, in step 18, any excess metal that isn't needed is carefully removed from the wafer. This leads us to step 19, where terminals are formed in the spaces left after removing the excess metal. These terminals act as the critical points for electrical connections. Finally, in step 20, we assign specific names to the terminals of both NMOS and PMOS transistors, which helps in identifying and managing the connections during further processing and testing. These steps are essential to ensure proper connectivity and organization in the finished semiconductor device. Here, we're focusing on the making of CMOS using P-well technology. The process is quite similar to the N-well process, but with a key difference. It starts with an N-type substrate, and P-type diffusions are performed instead. Despite this approach being viable, the N-well process is often preferred for its simplicity. Looking at the CMOS IC layout, the upper view shows the fabrication and layout details. You can clearly see various metal contacts alongside the N-well diffusions. These elements are crucial as they define how the CMOS transistors are interconnected and formed on the chip. This layout visualization helps us understand the physical implementation of the CMOS process and highlights the importance of well placement and diffusion types in device performance.